For each of the following, list the real zeros, state whether it crosses or touches the x-axis at each intercept, state the max number of turning points, and determine the end behavior of the graph. All right, so let's take a look at the first function, f of x. For f of x, the answer to part A basically is pretty simple to see since the function is nice and factored for us. Remember, if x minus the square root of 2 is a factor, then you can set that equal to 0 to find the 0, so it'll be that x is equal to the square root of 2 is a 0. Now, it's squared, so we're going to say that it has multiplicity 2, right? And multiplicity 2 means that we're going to have 2 zeros basically at that location, right? And then we look at this x plus 2 to the 4th power, right? Well, that's going to mean that x plus 2 equals to 0 is a solution of the function, or a 0. And that would imply that x is equal to negative 2 is a 0. And the multiplicity of that 0 will be 4. In other words, we have a repeated 0 there, and it's repeated 4 times. That gives you a total of 6 real zeros, but basically there's only 2 actual zeros that are repeated multiple times, right? So square root of 2 is repeated twice, and negative 2 is repeated 4 times. Okay, now from there it's going to ask us in part B, does the graph touch the x-axis at each intercept, or does it pass through it, right? So it turns out for both of these, it's going to touch and bounce off essentially. And the reason why that's the case is because the multiplicity for both of the zeros is even. So remember, if the multiplicity is even, right, that means that it's going to simply touch the x-axis at that location. If the multiplicity were odd, it would pass right through the x-axis. So basically, when the multiplicity is even, it almost makes the x-axis impermeable, right? The graph will hit it and bounce off. Whereas when the multiplicity is odd, then the graph will actually penetrate and pass through the x-axis. So it's kind of an interesting trait. All right, let's look at part C then. Part C says state the max number of turning points. Well, it turns out that we can tell the degree of the function here is 6, right? And the degree of the function is 6 because if you expand that out, you're going to eventually get an x squared from the first parenthesis, right? And from the second parenthesis, you'll get an x to the 4th, and then you have to multiply those two, and that's going to give you x to the 6th. So the highest degree term of the polynomial will be x to the 6th. That means the degree will be 6. And that means that the max number of turning points is basically that degree minus 1. So remember that the max number of turning points is simply equal to the degree minus 1. So in this case, the answer is basically 5. All right, and finally we'll do part D, which is to determine the end behavior of the graph. And all this is essentially to say this function is going to behave kind of the way x to the 6th would behave, because its degree is 6. What's a better, more useful thing, I think, is to say that because the degree is even, this graph will exit and enter the rectangular coordinate system in the same hemisphere. What I mean by that is that, remember, anything that's an even degree like that is going to kind of look something like this, right? But it could do some crazy things in the middle. It can do stuff like that, you know. But either way, what's important is that the end behavior is going to always be, in this case, coming in from the top and exiting at the top. Now, of course, if we had a negative sign in front of that, right, then it would do the opposite in the terms of it would do something like that, right? It would exit and enter the grid, right, at the bottom. But in this case, since the coefficient in front is positive, this graph is going to do something. Who knows what it does in here, right? But at the end, it's going to exit and enter from the top of the rectangular coordinate system. So that's basically what we can tell by the degree of the polynomial. All right, let's do the same thing then for g of x. All right, so for g of x, what are the zeros? Well, it looks like the zeros will be found by taking x minus 3 and setting it equal to 0, which of course gives you the idea that x equals to 3 is a 0 of the function. And then you'd have x squared plus 2 is equal to 0. And if you try to solve that, you'll get x squared is equal to negative 2. And if you take the square root of both sides of that, you're going to end up with the idea that x is actually equal to plus or minus the square root of negative 2. So therefore, plus or minus I square roots of 2. Now, the thing about this is these are not real. So if we're going to say that we're looking for real zeros, then those don't count. All right, so that means we only have one real zero, and that's x equals to 3. That's our only real zero. All right, and then it says, does it cross or touch the x-axis at each intercept? Well, we only have one intercept, right? X equals 3, because the other two zeros we found were not real. And at x equals 3, since it only has multiplicity 1, it will cross the x-axis, right? So it crosses at x equals 3. In other words, it's going to penetrate the x-axis there. It'll pass through it. For part C, it says state the max number of turning points. All right, so it looks like the degree of this function is actually going to be 7. Why do we say 7? Because, you have that x minus 3 in the first parenthesis. That x has a degree of 1, right? And then when you eventually expand out x squared plus 2, you will get an x to the 6th there at some point, right? X to the 6th times x is going to give you x to the 7th, so we'll end up with a degree of 7. That means the max number of turning points, right, will simply be 6, because remember, it's the degree minus 1, so we're going to say max number of turning points is equal to 6. All right, then the final part here is determine the end behavior of the graph. So this graph is going to kind of be like, what, 2 x to the 7th. And the reason why we say that it's going to be kind of like 2x to the 7th because there's a 2 coefficient out in front, and then we have this x to the 7th there, right? So it should be somewhat like that in the extremes. Now, the only thing to keep in mind, I think that's more useful, is that it's an odd degreed polynomial, and that means that it will enter and exit the rectangular coordinate system in different hemispheres. So what I mean by that is basically it's going to do something like this, right? Now, again, I don't know what happens here in the middle. It could go in all sorts of crazy things in the middle, but at the end, it's going to enter from the bottom and exit at the top if you're reading it from left to right, right? And that's basically it. So again, we know that strictly because of its degree, right? Think about the classic x to the 3rd graph, which has odd degree. It looks like that, right? And you know that x to the 5th is very similar to that. It's just kind of more flattened out, right? And so on and so forth. X to the 7 is also very much like that. It's just even more flattened out there in the center. But basically it's going to enter, as you read left to right, it'll enter from the bottom and then exit at the top here. And that's different for functions that have a degree that's even. All right, and that's basically it.